Hello, welcome to part two of our third lesson on electrical circuits. So in part one, we were looking at series circuits, and we're going to move on to parallel circuits. So lesson objectives are exactly the same, but the circuits become more complex. To recap our two rules that we must apply. So whenever we're looking at current, we need to make sure that the current's conserved. So whatever the current is at the beginning, we must have that much current at the end as well. And the voltage, that when we consider the path that a single electron is taking, we need to make sure that it completely uses up the voltage supplied by the battery. A parallel circuit is more complex than a series circuit. We mentioned in part one that there's no junctions in a series circuit. So the junctions are the key thing for a parallel circuit. There must be a split in the wire in order to have a parallel circuit. So this is an opportunity for some electrons to move one path and others to move a different path, and therefore we can make more complex devices. So going on to look at current in a parallel circuit, remember rule one, that current must be conserved. So if we start with 6 amps coming out of the battery, as we move down the first path, there is nowhere else for that current to go, so we must still have 6 amps at this point. However, we then reach a junction, and at the junction, some of the electrons will come across and some will carry further on down. But we've only got 6 amps to play with in this particular circuit. So obviously I'm just making the numbers up as I go. I'm going to say 2 amps come across sideways, and in order to conserve that current, the other 4 amps must carry on down the other path. So if we continue with the 4 amps, still nowhere for it to go along this path. So we've still got 4 amps. Goes through the bulb, still no junctions, so we must have 4 amps at this point as well. We then reach another junction. So the 2 amps comes across, the 4 amps come up, and they meet again at this junction, which means as we carry on further up this path, we then have 6 amps. So we are back to our original current, therefore the current's been conserved, and therefore we've done that circuit correctly. Looking at voltage in a parallel circuit is probably the most difficult part of dealing with current and voltage in circuits, because it does become more complex, and it's important to think about rule 2 and make sure we're thinking about one electron at a time and the path that that electron takes. So I'm going to label the battery up as 12 volts, and that means any individual electron coming out of that battery has a potential of 12 volts, and by the time it gets all the way around to the other side, it needs to have 0 volts. So it's important to consider how many different paths there are through the circuit and deal with one electron per path. So for the first one, I'm going to deal with an electron that's going all the way around the outside and how that one's going to behave. So that's the route our first electron's going to take. It's got 12 volts, and by the time it gets over by here, it needs to have 0 volts. And there's only one opportunity on this path to get rid of the voltage, and that's this bulb at the bottom. So that bulb must take all of that electron's voltage. So that would be a 12 volt bulb. Another electron will also start off with 12 volts, but this one happens to come across the middle path. So through the bulb and through the resistor and back. Again, it needs to have 0 volts by the time it returns to the battery, but this electron has 2 opportunities to get rid of voltage. So therefore, it's going to offload some of it in the bulb and some of it in the resistor. Now, as I mentioned in part 1, for an exam, you probably have one of these labelled and then have to work out the other one. It might also say that they receive identical amounts of voltage, in which case it would split evenly. But as long as your values add up to the required 12 volts, then you shouldn't go far wrong. So I'm going to say that this one gets 8 volts, which means that this resistor would then receive 4 volts. So as the electron comes into the first bulb, it's got 12 volts, 8 gets taken. So by the time it's by here, it's got 4 volts left. And then as it comes out the other side of the resistor, those 4 volts have been taken by the resistor, so it's got 0 volts, and it's happy to go up the wire and back to the battery with no potential left. So you can see that the series circuits are far simpler than parallel circuits, but as long as you get used to applying those two rules, they should be straightforward. And when it comes to our examples, again, you need to split them into dealing with the current first of all and the voltage afterwards. So as I mentioned in part one, the arrowheads usually indicate where the WJC want you to label a current, and then any components they want you to label usually either have a little answer line or a box next to them for you to fill in. So we're going to deal with current first of all. So you can see we've got 6 amps coming out of the battery, reaches the first junction, and 3 of those amps carry on along the wire. That must mean that 3 amps head up this path. Okay, and we'll reach the other end because there's no more junctions. Those 3 amps then come to another junction. 2 amps carry on, which means 1 amp must go up this path in order to conserve it. And then by the time they reach the other side, they're all on their return journey. So 2 amps will carry on around this path until it reaches this junction. The 1 amp will carry on up here. So the 1 amp meets the 2 amps and they start heading back then together as 3 amps. Those 3 amps then reach our final junction on the return journey. They meet up with the 3 amps that headed up this path, join together, and the 6 amps head back to the battery. So again, we've managed to conserve our current. We started with 6 amps and we've ended with 6 amps, so we've done that correctly. We then need to look at voltage, and as I mentioned, we need to treat every path with an individual electron that's carrying the voltage of the battery. So an electron that's carrying 9 volts has 3 options for this. Okay, and to keep it a bit simpler, I'll do them in different colours. So the first option is it goes all the way around the outside, the long route. Now on that path, there is only one opportunity for the electron to get rid of its voltage, and that's at this bulb. So therefore, this bulb must get all 9 volts. Then going to look at an electron that travels down the middle path. So second electron starting with 9 volts. This one moves down the side to the second path, up that second path and back. So following that path, there are 1, 2, 3 bulbs on it. So they are the only opportunities to get rid of the 9 volts. So those 3 bulbs on the middle path must add up to the 9 volts. We've already dealt with 3 volts in the middle bulb, 1 volt in the top bulb. So therefore, this bottom bulb must be 5 volts. Okay, because 1 plus 3 plus 5 gives us our total of 9 volts that needed to be used up. We then finally consider the last path, which is up through these 2 bulbs. And again, our electron starts with 9 volts. It's only got 2 opportunities to get rid of the voltage, okay, in this first bulb and then in the second bulb where it gets rid of 2 volts. So if the second bulb has 2 volts, the first bulb must have received 7. A final worked example to look at for this is a more complex one where the WJC are trying to challenge your understanding a little bit, and it's when they include a bulb that's on both paths. So this bulb occurs before the junction, so therefore an electron going around the outside will pass through it, and then a separate electron going up the middle path will also pass through it, and therefore it needs to be taken into account for both paths. And this often confuses people. So the easiest way to do it, if written off to the side, is to look for the path with only one unknown voltage. So I'm skipping current for this because I think current is fairly straightforward. We're going to look for the path with the least unknowns, and that is the longer path around the outside. So as we travel that path, we've got one unknown bulb and then 2 more bulbs that are already labelled up. and then back. Whereas the middle path, we got one unknown bulb followed by another unknown bulb. So you can't do that red path to start with. You've got to start with the green path. And then we're applying our rules, thinking about an electron that starts with the voltage of the battery. So it starts with 6 volts. It passes through this bulb to use some. Then it passes through these using 1.5 and then another 1.5. So these two bulbs use up 3 volts collectively. So therefore, this initial bulb must also use up 3 volts to get rid of all 6. Only then, once we've completed that bulb, can we consider the second path, because now we've already done one of our unknowns, so there's only one unknown left on the red path. We start with our electron with 6 volts. As it passes through that shared bulb, it uses the 3 volts. So therefore, it's only got 3 volts left when it passes through that second one. So to see whether you've understood this, I've put another sheet on the assignment for you to try. Obviously, these will be more difficult than the first one. So have a go at those and let me know if you're having any problems. Thanks.